Welcome everyone to the first talk of the Arithmetic Geometry Seminar this semester. I'm very happy to have Pierre Deligne explain new tensor categories to us.
So I think I will start with some pre-story of the impact from in the world. So the first thing was Pretannakian category. And this was introduced by Grothendieck for its theory of motive. And so let me tell you a little the idea of Grothendieck. In algebraic geometry, one has quite a number of cohomology theories for algebraic variety, the Harman, melodic, crystalline, and they all look the same. And so the basic philosophical idea is that it should all come from some object which has some integral flavor. And for the case of H1, this can be done for projective non-singular variety. We have the Picard variety, from which you can deduce all H1 in all those cohomologies. And in some way, the idea that there should be something unifying those theories occurs somewhat in some old paper of André Weil already. He observes that using odd theory, if you have an algebraic variety over C, to each odd cohomology group, you could attach an abelian variety. But this is no good, in fact, because it does not depend analytically on parameters. It has no good property as to the field of definition. And then the idea of Grothendieck was a very simple idea and completely unexpected, that one should not try to define some object which give rise to all those incarnations. One should try to define, so not object, but a category. That the thing to define was the category of motive and what he calls Faber-Fonter, which then gives the various cohomology theories. So what kind of category does one want? First, it would be an abelian category because that's what all those targets are. But the crucial additional thing is that you should have a tensor product, for instance, to be able to formulate Q-net formula in the motivic setting and then having it in all theories out of that. So Pretannakian category are the type of category which that kind of motive should be. So it's a abelian category. You have a tensor product, which is associative, commutative, which unit. All those are data, not properties. Then every object should have a dual, and here I want to precise what I mean by dual of an object. You want to have an evaluation map, dual of x tensor x going to the unit object. You should also have a co-evaluation map, one mapping to it, and then composite map we build with those. So here you, x, yes. X is one tensor x, one you map here, and now you use the evaluation cell, and this would be the identity, and something similar where you start with x dual. And then for Pretannakian case, there should be realization Fonter, like you had for the various cohomology theory, to vector space possible. Yes, there should be a ground field, K, and endomorphism of the unit object is K. For the case of motif, K will be Q. but Faber functor can be with value in a vector space bigger than K, and that is compatible with all those data. And then, now let me suppose that the ground field is algebraically closed, and then there is a kind of dictionary between Pretannakian category and affine group scheme. If you put some finiteness properties, it will be linear algebraic group. So if you have a linear algebraic group, things SLN, SON, anything reasonable, you can look at the category of n over some field K, E algebraically closed. You can look at the category of representation of this group, and it will be a category like this. And then the theorem is that it's a dictionary. If you have a Pretannakian category, you can put it in this form, and the group is essentially determined up to inner automorphism, is determined up to inner by the category. So we have this kind of dictionary. Now, if you want to, here one of axiom, there exists Faber functor. Morally attaching to each object underlying vector space. Now, Pretannakian you will just drop this condition. And so, in a way, if we view Pretannakian category as being essentially the same as linear algebraic group, Pretannakian category are a generalization of linear algebraic groups. So that's one, yes, and one thing which will be useful later. If you have a Pretannakian category, you can define the dimension of any object as being an element of the field. You have identity going to X tensor X dual, which goes to X dual tensor X, which goes to the, because it's commutative, goes to 1, so, and so you have this composite endomorphism, an endomorphism of 1, which is an element of the field. And so this is for the dimension X. So that's one source. Another source, maybe I am a little historical here, is the dimensional regularization of the physicist. So a strange idea of the physicist, they want to look at some integral, some Harman integral, and it diverges. So you want to attach some finite value to it, and the idea is that you look in dimension different from 4, what is happening, and then sometime it will make good sense. So, and you have a formula for what happens in dimension D, which makes sense for any real number. And then you try to put this real number equal to 4. Often you will have a pole, you will need to take a finite part, and then you get a number. So at least what this suggests, when you have construction making sense for some integral dimension, it can be interesting to try to make sense of it for a dimension which is not an integer. And this is one way of doing this. In usual setting, dimension is an integer, and here it has no need to be. And this leads to the idea, for instance, of defining category of representation of GLT. So GLT has no meaning, but you can define what should be the category of representation of GLT for any T. That's one second source. Then a third source so that's physicist. third source is an observation of Vogel, which in fact leads nowhere, but still, for me, it was important. So, I don't know how much it was joking, but Vogel was telling that there are 12 series of simple reductive groups, A, B, C, D, and the exceptional series. So this suggests that there would be something depending on a parameter T, which gives for a specific value of the parameter all the D2, N, and so on, and a few others. And to some extent, to the very beginning, there are things interesting in telling it works. So if you take one of those exceptional groups, you have something called the dual Coxeter number. The definition is not important. And then you can look at things like the Lie algebra, it's tensor square, it's tensor cube, see how it decomposes into simple representation, what happens is that the decomposition is the same for all G. And if you look at the dimension of the representation, it's given by, as a rational function, relatively simple, of this parameter, which in addition is a ratio of product of linear form, a little like to get this kind of nice formula. So for a while, I was very optimistic one could do something like that, but it seems to break down when you go to the exterior power of G, becomes completely not understandable. So I don't believe it works, but it was a reason to look at Pretannakian categories. Now, to explain the new idea which has led to very new Pretannakian categories, I will explain one case of interpolation, how to construct the categorical representation of the symmetric group Sn when n is not an integer. In the same way that for GLN you want to allow non-integers. So instead of Sn, I prefer to speak of Si. I is a finite set, and you look at the group of permutation of this finite set. Now, let me first look at some transitive Akfanon sets. So if you have a finite set U, you can look at all the inversion of U into I. Let me call this U. And so this is an homogeneous space under this symmetric group. And now the kind of thing which happens is that at least when I is sufficiently bigger than U, the category of those homogeneous space or product decompose, it's all independent of E. So let me give an example. You take two finite sets, U and B, and look at their product. So what are you doing? You are looking at a pair of injection, U to I and V to I. and you are wondering what is the orbit of the pair FG. And it's easy to see that it depends only of the pattern of equality. You can have when some f of u is equal on some g of v. So one way to formalize that, if you have a not a finite set which invert into I and v, you can make an amalgamation of E and V by identifying A, which is in both. So this tells a pattern of equality between some f of u and g of v. And what you have is that this is equal to this one sum for all those amalgamation of I and v over something you decide to be common to some of W. And I will possibly use it later. We have something similar if you look not at product, but at Faber product. And of course, if U is too big, then what you get is empty. You will get no injections from U to I. So what I am telling here works fine as soon as I is big enough with respect to the U you are considering. And another property where the same unit a little bigger, you can wonder what are the maps from as a symmetric group homogeneous space from one subset to another, and you see it corresponds one-to-one to inversion of V into U. If you have a map of, sorry, yes, yes. If you have a map from U to I, you can restrict it to get a map from V to I, and it's the only way as soon as both, as I has at least two more elements than both. And another property is that if you look at the number of elements of this set, it will be given by a polynomial formula in terms of the cardinality of the set I, because you want to count injection from U to I, you order U, the first element has to go somewhere in I, the second one has to be go somewhere, but not where the first one went, up to. So this is polynomial with integer coefficient, with coefficient in the cardinality of your set I. And you will easily check that if you look at the cardinality of the Faber of any point here, you will have a similar formula, because the Faber, the cardinality is the quotient of the cardinality of this by the cardinality of that, because it's homogeneous. And you look at the quotient of those two polynomials, it will be a polynomial again. Okay, so that's one. Oh, yes. Now, yeah, I have steps, but I want linear representation. No, from a set on which symmetric group act, I can look at the Q at the power of this set, so the vector space with basis the element of this homogeneous space, and this will be a linear representation. And now, if you want to look at, and let me call this U in curly brackets, so you may want to compute homomorphism protraction of the symmetric group from U to V. So this will be given by some kernel K F V, where F is an element here and V is an element there. And you may speak of matrices instead of kernel if you prefer, it's the same. But that's any morphism from this one to that one. You want invariant by SI, so you want this kernel function to be invariant by the action of SI. So a basis corresponds to orbits of the symmetric group in U times V, which we have seen is something independent of the cardinality of I. So you have that this Hom group has again a base independent of I, at least if I is big enough. And this base corresponds to all possible amalgamation of the sets U and V. So you have some objects. We will need more, but at least some object to start with. You have Hom groups, which are given with some concrete base. You have a category, I still need a composition. So what is it in that case? If you have two kernels, KFV and KH, I need to look at the sum over G, K, F, V, H. So what does this look like? Yes, I am now using double. You see that amalgamation will be called X instead of W because I have three objects and I keep W. So what do I have here? And suppose I have a basis element in the Hom group to the characteristic function corresponding to some amalgamation X. And here, let me take a basis vector also in the Hom group corresponding to another amalgamation. So I have this X mapping to U and mapping to V. I have this Y mapping to V and mapping to W. And I am interested, and so yes, I take as basis element the characteristic function corresponding to one of those orbits of the symmetric group acting on U times V. I care about triples FGH, where FG is in X and GH is in W, so it means I want to look at the Faber product of those two. And now this Faber product maps to U times W. And what the formula means, the kernel I want for each FH, I look at the cardinality of the Faber. Now, Z will be a copies of homogeneous space corresponding to some W's. What I was telling for product, one can repeat for Faber product. And if I have a basis element here, sorry. Then what I need to know is the cardinality of the fiber. And as I have explained, this cardinality of the fiber is given by a polynomial in the cardinality of my set. And then I replace this cardinality by an indeterminate, and I have a formula for the kernel. And because it is associative, whenever this cardinality is a big integer, it will always be associative. Now, one needs more to have, so here I would have a category. One needs to define the tensor product. It's still not good enough. One needs to add image of idempotent elements, so this can be complete. And then one has to prove that one has a Pretannakian category, at least if t is not the parameter is not an integer. So that's what was done long time ago. And now I want to explain how Harman and Snowden look at this in a different way, which allow for interesting generalization. So the idea is that instead of a symmetric group Sn taking n variable, one just takes the infinite symmetric group. So one now takes the sets, an infinite set, and corresponding symmetric group, and there is some flexibility. You may take all permutation of the set. You can take those with move only finitely many elements, and in the end it will not matter. And this kind of detail being not important will be true in many similar situations. Now the point is that you still can define the homogeneous space of maps, of injective map from U to R. You still will have the same composition for product of two such orbits. Yet one thing which one may observe and here or there is that there is a characterization of those particular homogeneous space I was using. For any integer n, you can look at the Cartesian power of I and look at what orbits you get for the action of the symmetric group, and you will get things of that type. If you take the orbit corresponding to distinct points, you see you will get the set of distinct points as your U. If some are equal, you take only one of them for each bunch of equal points. So you have this, you have the same formula for our product also. So you can define, you decide that you want now to have a category K-linear with object corresponding to those finite sets. And inspired by this, you know what you should take as home group from one to another. Now you have the same problem as before to tell what is the. You think morally as this home group to be given by a kernel KFG as before, where the value of Fg depends only on the orbit in which Fg lives. And now you have to make sense of this formula because you have an infinite sum now. But if you look at what is done here, what you need to do is whenever you have a morphism from some of those homogeneous space to another, you have to give a prescription for what you will call the number of elements of the fiber. So this will be called a measure. So for each morphism between homogeneous space, something you label as being, you will call it, call it mu of u. And it could satisfy some property so that the associativity holds true. And so one can look what property one needs to have associativity, and I just give the result. We just state the important property. There are some stupid ones like isomorphism. If you have something isomorphic to U to V, it should be the same. So let me just tell the identity fibers would have one element. So, but the important thing is that if you have composite map, then what you decide to call the number of elements of the fiber from ear to ear is the product, the similar thing from ear to ear and from ear to cell. So that's one property. The other property is that you have U to, sorry, and now you take a change of base, so a fiber product. Now this will not be just one orbit, it will be a sum of a number of orbits. So this is the fiber product. And here we have a number of elements of the fiber. You want the same here, where you decide that if you have a few orbits mapping to something, the number of elements of the fiber is the sum of the number for each constituent. And you would have that the number of the element of the fiber here is the same as the element of the fiber after pullback. So the formula is that sum of mu for V is the sum, the number of elements of the fiber for those W2. And then you will get associativity. Here, so again, here one has just a category. That's not enough. One needs to define the tensor product. One needs to add some direct factor corresponding to idempotent, and then one needs to prove something to have a Pretannakian category. That's not obvious, but now the good thing about this change of point of view is that before you had a number of groups, and in some ad hoc fashion you interpolate. Here we have just one group acting on something, and you are asking to find a measure in this sense with a number of properties. So you can now start with your preferred group acting on something. The key property to make sense of things here is that you have a group acting on something, and if you take any Cartesian power, finite power, the there would be finitely many orbits. And in this, this is what they call oligomorphic action, and an example is symmetric group of an infinite set. So the change of point of view is that you have some object and then a concrete question trying to find all measures in a given situation. It's not easy to do, but it's a well-defined problem to which you can find surprising solutions. So I will give some of the solutions which have been found. The one which for me is the most beautiful is in a paper of Harman, Snowden, and Snyder. I start by describing what is the whole of infinite symmetric group acting I. So here you take R with the order relation and the automorphism of this object. So the group of all increasing Bitvector from R to itself. So and acting on R. And it's easy to see that all, if you look at a Cartesian power, so you look at an element, you look at the orbits, you will see that they are all obtained as follow. To take a finite set with a total order and all injection from U into and all orbits on some power of R will be increasing injection. So two increasing injection will be conjugate by a bijection of R with respect to order. Take a linear interpolation, for instance. Now, here is the surprising measure you can construct. You see that all of those are very simple topological space. They are just cells, in fact. And also, if you take, so theta will pull again U, not the same as before, it's increasing injection now. And suppose, and yes, and also would say that to get a map from U V, you should get increasing injection from V inside of U. So then you restrict and you have a map. So suppose you have a map from U V, and you want to count in some way the number of elements of a fiber. Note that the fibers are very simple. They are just cells again. And note what you do is you look at the earlier Poincaré with compact support of a fiber. And earlier Poincaré with compact support has very nice additivity and multiplicativity property. For instance, if you have a composite map, the fiber for the composite will be a fiber ring again, where you have for the first map and the second map, and you have multiplicativity in this situation. When you take a pullback, maybe I would think to it as a fiber product, then again, the point is for Euler Poincaré with compact support, if you dissect something into disjoint pieces, you have additivity of Euler Poincaré. So this will be a measure. And after some work, one check it gives us to a Pretannakian category which has mirific properties. So first it's a semi-simple abelian category, which you obtain. The dimension of any object is plus or minus 1. Recall you that dimension is something defined when you have a notion of dual. Here, those objects are self-dual, so, and as you only add direct factor, every object has a dual. Then I was working all the time on characteristic 0, I should have said so. And then it's easy to define the exterior power of some object because you take the tensor power and then you have the antisymmetrization, and that's a projector, and you take that piece. So you have exterior power operation. With that, if you look at the K group of the category, it will be a lambda ring. So you will have all the things you have to do with lambda ring, including Adam's operation. And the Adam's operation will be the identity. And that's about the only case, I think it's the only case I know where Adam's operation are the identity. Oh yes, and also they make a very detailed analysis of this category, which they call Delanois category. For example, they can describe all simple objects and how a tensor product decomposes into simple objects. There is another category which I like very much, which was invented by Sophie Kriz, which is, if one thinks to this as sets, we go to vector spaces. So the analogy which one wants, on the one hand, you can look at the finite set totally ordered. Or you can look at a vector space given with a complete flag. And we play with this analogy. So let me describe first the space on which the oligomorphic group will act, and then what the oligomorphic group is. You again start with R. But now, it's not on R you will act, but you consider direct sum of copies of F2, finite field, indexed by R. So it's the infinite dimensional vector space with a base indexed by the real number. Here also, if you prefer rational number instead of real number, it will not matter. If you want, yes, I did not say what automorphisms are. Yes, now here you have a number of subspaces. For any real number R, you can look at the subspace FQ at the power the semi-infinite interval up to A. And this family of subspace is somewhat like a complete flag. So you have two infinite bases and you go up to somewhere, and those are the subspaces. Now, here I have indexed this by R, but I will forget this indexing. So now I consider omega with the sets of all those FA. So that index complete flag. And then my group will be automorphism of this object. So there are two kinds of automorphism. First, if you have, as before, an increasing bit vector of R to itself, clearly I have used, to define the FR, I have only used the order, so you will have this kind of transformation. And also, if you have some basis element EA, you will be able to map it to a multiple of itself, not zero, plus things coming before. So kind of, I think at this to a complete flag, and if, and I can look at the lower triangular matrices. So that's the group, and again, one easily see that if you take power of omega, there will be finitely many orbits, and the homogeneous space you get indexed by a finite dimensional vector space with a complete flag, with the orbit being alter map from V to omega, so that if you induce this flag on V, you get the complete flag you started with. So it's completely parallel to the previous case where one had an ordered set and one wants a compatibility for the map. And now the surprise is that, again, you have a measure. Let me, yes, I could tell it in general. So if I have a vector space with a complete flag, to it corresponds some orbit, and the number of elements of this orbit will be over Q minus 1, that's the power of the dimension of these vector spaces. And so this will give a measure. So we don't know as much here as we know for the Dollar category before, but at least we have this measure and a little more. We don't have a classification of simple objects of the corresponding abelian category. The computation is a little painful, but there is an heuristic which gives this result, which I like. I would like very much to be able to use this heuristic to make a proof, but I am not able to. And this heuristic works in other cases. I will, for instance, here I can look Fn, and so I have something like an infinite version of a parabolic subgroup, which I am considering. There also one is a measure one can have. One can take something infinite here. Again, not a version of a parabolic subgroup. And here one will have a measure depending on a parameter, like we had for the infinite symmetric group. But let me just give the heuristic in the simplest case where I take a V of dimension 1. In that case, the orbit is very simple. It's full vector space. The condition now for D of dimension 1, I have just one complete flag on it, and there is no merit for the flag I have on omega to induce it. So I am just looking at injection from this V to omega. So this means a non-zero element in omega. So I would first ask how many elements do the measure. Yes, one thing I should have said, I always spoke of measure for the number of elements of a fiber. But if I take just some orbit, I can map it to a point, and the fiber is the orbit itself. That's what I will call the measure of this orbit. And often one can recover one from the other. So here I am just going to consider what I want to call the number of elements of omega or of omega minus 1 part. Now, first, the number of elements of omega. So it's a sum of copies of FQ indexed by R. And what we have seen in the previous story of the Delano category, as chi of C of R is, sorry, what? Then say something. Yes, it's minus 1. This suggests that one should view R as a set with minus 1 element. Now, if R is a set with minus 1 element, omega is a vector space with a base with minus 1 element, and so it should have as number of elements 1 over Q. Now, I don't want all of omega, I want to subtract the 0 elements. So I subtract 1, and this is what the answer is. And the same heuristic works in those other cases I was explaining to guess what some method would be. There are other kinds of examples which are quite fast using trees, and then it leaves a question of combinatoric about trees, but this I will not explain, and I will stop here.
Thank you. Further questions?
So what's the rigorous definition of this mu? Mu of these?
So I want to define a measure. So measure is, I first define it as something which to any map of homogeneous spaces attach a number. So here I want a single space. So I look at the map from this homogeneous space to a point, and now I am in the setting where I speak of the, so by definition, mu of an homogeneous space is mu of the map from mu to a point. And when those numbers are not 0, one can recover what one wants for a map, because if you have a map from U to V, then you will want that to this map correspond to quotient number of elements in quotes of U divided by number of elements in quotes of V.
But then what's the definition of mu of
No. What I claim is that if I take this as definition of mu, then all the properties which I have listed, which enable me to define a category, holds true for an inter-associativity of the composition.
What about the converse? So like you've given examples of measures satisfying the axioms.
Yes.
You say that all measures satisfying the axioms are of this form, or are there lots of other measures on these categories satisfying the axioms that aren't the ones you wrote down?
I think for this one, it's essentially the only one. For the case of the infinite symmetric group, I think also. So in a number of cases, one can, and then one can, one thing which can be useful, instead of wanting to compute all possible measures, one can look at those axioms one wants for a number of elements of a fiber, and now define an algebra where those are the generator, and you put the relation which were needed, and then trying to compute what this ring is. And this has been done in a number of cases. In a number of cases, you will get something nice like this, plus some degenerate things. But so in a number of cases, one knows exactly what is happening. And in fact, this ring is useful because Snowden, Snyder, and Harman, in terms of property of this ring, give a criterion so that we know we get a semi-simple abelian category.
This last category you described, is that just semi-simple?
Yes.
And how do you prove that it's semi-simple without computing the simple objects?
I think in that case, one can use this criterion of the three people. If you can compute this ring, which now in this ring, you will need more than this because here you have only some orbits, but you may want to divide this orbit by some group of automorphisms to be in the setting which is needed. And then so you add some fractions, you divide by some power of q minus 1, I guess, in that case. And then there is a criterion of the three people. If you have enough maps to finite field, then you will know that you have some, and also if two things, enough maps to finite field and all dimensions of objects are not zero. That's morally the main thing you want. You want to avoid object of dimension 0. If you have an object of dimension 0, you have no hope of being semi-simple, because if you take x dual tensor x, you have one inside it, one mapping to it, but it does not split. But hopefully one has a converse. It's not true, but one has tools to have the converse proved sometime.
I have a naive question. So this provides many new examples of semi-simple Pretannakian categories. Is there any hope that you can discover all of them?
We are just exploring. I think that's too optimistic. So, and in many cases, there are a lot of variants one can identify also. Like I was using R with its order, or Q with its order. Now you can, in addition, give a coloring with a finite number of colors, where the element of a given color are dense. And you can with this additional structure. So there are many variants. So there is no hope so far. It would be nice to be able to describe all the semi-simple one, but that's out of reach. One thing I would have said also is that characteristic P has a very different flavor, and an example were known much before, the Verlinde category. This is rather different, but even in characteristic 0, hoping to describe in some sense all semi-simple Pretannakian categories, out of reach. We are still exploring what is around.
All right, if I have no more questions, let's thank the speaker again.